I mean, we do like, as a painter, it's, I just picked up a new kitchen from IKEA. It's in the back of my car. You know how IKEA, like, they never solve their logistics problem. Since COVID. Like you can't actually order things. You order stuff and they don't even promise. Like they say, oh, you just order and then maybe something's come like really want that. So what you have to do is like you have to order from the store. And so what I needed, I could get in like two different stores. The other in Starbucks. So in a way, I'm just like, pick this up. Because I don't want to put in an order and wait for 3 months.
Yeah, yeah.
This looks like the first. I can't do so.
What did you order?
No, just cabinet, basic ones. We always say it's temporary, but the more it looks, it's like less appetite we have for more. The units are very good.
I think we're actually gonna read it.
But you must be happy, because I remember a month ago.
Great.
Yeah, this one is.
I think you can. It's like a little. Almost everyone else.
Right. That's cool.
But I hope they have it in stock.
Yeah. So these are just order online, because that's the one where you can find. But you can order the store and then sometimes they can put it in the locker there. That's the best. Because then you just drive there, put it in your car, drive back.
That's the closet.
Okay.
Nice.
That's right.
Really organized. Listen.
Hierarchical society. It is, like with us now in CMS, we had to have to accept these 100 new students. And the dean came today. It's like tough labor. She says, you just have to do it. It's like, well, sorry. We're like complaining. And she's like, sorry.
What do you have to accept?
100 students into CS.
100 extra.
Yes,
This is because the government wants it?
because they have a 20 million budget, sure. And this is how she decided to solve this thing. Like she knew she doesn't have that many options. I think the only other option, because I was thinking like she just came like this summer. So I don't think she can start firing.
Yeah.
And that's in that situation. Like you have to be around for a while to start firing.
20 million.
And no other department have applicants for reasonable.
Yeah.
So it's like author management. So the only reason we can be upset is that it wasn't management is not pushed that much. So
100 students isn't getting $20 million for what's that?
So how much does it get? I think it's 40,000 per student. So
Okay.
so how much is that?
$4 million. Yeah, that's
4 million. So
it's part of it.
yeah. And then if it's foreign students, it's maybe even more. The government gives you 40 per student. That's what I computed from what she was telling us. But then she said that they were actually not as bad as other places, and that most of it is because of India. I think. So the students from India are not coming in the numbers that they used to.
Isn't this because of the federal government cuts
So it's not clear. So it could be,
Applications.
right, but
Applications are what?
I think it's
Applications are
down.
across.
I think it's because of the political, mess up with India. There's, that's my feeling.
But I thought Trudeau was so stupid to pick his price. But
Like why?
actually, the Americans essentially picked the same hybrid. So,
But it's okay if you do it in certain American,
yeah.
because then you have some strength behind it, right? If you don't have the strength, then why do you? But also, I mean, right, I mean, they had people assassinated, right?
Yeah, oh, yeah.
In Canada.
No, I mean, it is
So-
a
so-
real
so-
problem.
So yeah,
These guys really did send agents to kill people.
yes. Thanks for the.
Yeah.
Very cool.
This is the other phase. Okay, we're very happy to have Justin Coe from the University of Waterloo, who will talk to us about pseudo-maximum likelihood theory for high dimension rank 1.
Okay, thank you, Duncan, for the introduction, and thank you everyone for showing up. There's lots of familiar faces here. That's nice to see. I'll be presenting joint work with Curtis Grant, who is a former undergraduate here at the University of Toronto. Bokash Jagannath, which is my current postdoc supervisor, but he was also a postdoc at the University of Toronto, and myself, a former graduate student here. So let's begin with the problem. So in one sentence, what I'm interested in is I'm interested in the inference of low-dimensional structures hidden in some high-dimensional noise. And this will be illustrated through two examples. One is a spike matrix problem, and the other one is a community detection problem, which I will sort of go through in detail right now. So in the spike matrix problem, our goal is to infer a n-dimensional vector x0. This n, you can think of it as a very, very large number tending to infinity. I want to infer this n-dimensional vector from a n by n noisy matrix. And this n by n noisy matrix will be constructed as follows. So we first begin by constructing the rank 1 matrix associated with this vector. It's going to be XX transpose. There's a square root of lambda parameter in front. This will encode the size of the signal. It is just a fixed number that does not depend on n. And we're going to divide it by 1 over square root of n, which will force the operator of this matrix to be of order square root of n. We're going to add to it a symmetric matrix of IID entries, where they have a symmetric Gaussian matrix of IID entries with norm 0 and variance 1. And this is where the scaling in front of the X0 matrix is important. It is so that the size of the signal matrix and the size of the noise matrix are of the same scale, in the sense that their operator norm are both of order square root of n. And we're going to add these two matrices up, and we're going to define this matrix Y, which is illustrated on the right-hand side. And the inference problem goes in reverse. So the inverse problem is we are given the data matrix Y, and the goal is we want to recover what the matrix X0 is from this noisy observation of it. Okay. And in the second inference problem, I want you to keep in mind is a community detection problem. And in this problem, it's a very, very similar step. Instead of inferring a vector of size n, we want to infer communities, which is X0, which is encoded by a vector of entries of plus or minus 1. Plus and minus 1 encode which community each vertex belongs to. We can observe this from an adjacency matrix, which is a matrix of 0 and 1 entries. And this adjacency matrix will be constructed in the following way.
So there are only two communities?
For this problem, yes, only two communities for this one. Okay. So we have n vertices. We're going to label these communities +1 or -1. And we're going to attach edges between vertices according to the following rule. So we're going to attach edges according with probability 1/2 plus square root of lambda over square root of n if the vertices are in the same community. And we're going to attach an edge with probability 1/2 minus the same factor if they are in different communities. So there's a very, very slight bias in adding edges to vertices that belong in the same community. And the inference problem goes in reverse again. So you have a vertices, you attach edges, and the inference problem is we're given the adjacency matrix for the corresponding connected graph. And you want to infer from this adjacency matrix the labels +1 or -1 of the vertices. So these are the two examples I want you to keep in mind. And really, both of these examples are in some sense the same example in the sense that they fall into the same generic framework. And this is the framework we're going to be thinking about. So for the rest of the talk, we're going to define our latent variables x0, which are the variables we want to infer. These x0s will be a n-dimensional vector, and their entries will be supported on some compact set omega 0. So the second one is +1 -1, and the first example, it could just be -1 and +1, the interval. And we're going to observe these latent variables through a noisy observation of it. This will be called the matrix Y. And this matrix Y will be a symmetric matrix of order 1 entries. And the entries of Y will be generated independently, but conditionally on the latent variables through its rank 1 matrix XX transpose. So our notation is the entries of Yij will be generated conditionally on this probability measure P of Y, and it's going to be dependent on the corresponding entries of my rank 1 matrix Xi, Xj. And our two examples that we did before are constructed as follows. So in the spec matrix example, our entries Yij is constructed from a normally distributed random variable, where the mean of the normally distributed random variable is given by square root of lambda Xi, Xj. And in the community detection problem, the entries of Y is a Bernoulli matrix. So it's 0, 1 with probability 1/2 plus some correction term if the vertices are in the same community. So these are the two matrix examples that we want to keep in mind. And our goal is we want to infer what the variable x0 is. And already you can see that this is kind of a tricky problem because Y depends on the latent variables through XX transpose processed through another conditional probability measure. So it's not quite, or it's not so easy to figure out what's the dependencies or how do we get x0 from Y. So we're going to have to use a few techniques to solve this problem. And the focus of this talk is we're going to study a class of statistical estimators based on maximum likelihood estimation, which is what I'm going to define right now. So in maximum likelihood estimation, we're going to have our log likelihood function, which is the log of the conditional probability. And the likelihood function, just because the entries of Yij are generated independently conditioning on the x, it's going to be the sum of the log likelihoods. And our estimator is we fix a Y, and we treat our log likelihood function as a function of the x. We want to find the parameters x that maximize the likelihood of this observation. So you'll find the x that makes this log likelihood function the biggest possible value. And their estimator will be precisely the maximizer of this log likelihood function. Okay. So this is the class of estimators we want to see, and this is sort of will be our statistical guess for the underlying latent variables. And there were two words in my title. One was maximum likelihood estimation, and the other one was pseudo-maximum likelihood estimation, which considers the case where our information is not perfect, so we have to prescribe our own statistical model. So for this, the likelihood function g might not be equal to the true way the data is generated. It is something that the statistician may pick. And we may also misspecify what the parameter space is. So our omega might not be the same as the support of the latent variables. And this is called pseudo-maximum log likelihood estimation, where you have the same function, except now the law of the Y is not the same as the function that generates it. But in the end, we want to do the same task, is that our statistical estimator will be the choice of parameters that maximizes the likelihood of a certain observation. So these are the models we are looking at.
Why is this a good way to do things? To estimate?
Oh,
Why is MLE good?
it is a classical technique, I guess. I guess this is one of the ways that statistician does it. Why is it good? I think it's a very natural estimator in the sense that you are given some observation Y, and you want to find the values of your parameters that sort of makes this observation of y the most likely happen. So I think it's a natural estimator in some sense, and it's also a classical estimator.
I lost what's G as opposed to G0.
Oh, I see. Yeah. So G0 is the log likelihood of the law of y. So G0 corresponds to how my data is generated. But when we build statistical estimators, we might not know the distribution of the data. So for those, you have to specify another log likelihood. It's sort of like a model selection in the sense that we think this is what the true way y is generated, and we maximize that function instead. So it's there may be some mismatch in what we know and what's the true model. Okay. Yeah. So we are interested in the performance of these estimators, and we'll be measuring performance through a quantity called the cosine similarity, which is the normalized inner product between our estimator x hat and our true latent variables x0. So this measures the angle between between our guess and the truth. And if this is close to 1, it means that we have really recovered what the x0 vector is. And if it's 0, then it's sort of perpendicular guess that we haven't done anything. So this would be our measure of the quality of performance. And one question is, well, we also want to see the impact of model selection. So what happens if I misspecify what the log likelihood is? If I choose a incorrect log method, I want to compare what's the cosine similarity between various model guesses with the maximum likelihood estimate, which is we have used the correct log likelihood for that case. Okay. Good. So let's make things a bit more concrete and go back to the examples that we had before. So in the spec matrix example, we have our data y is generally conditioned by adding Gaussian noise to a rank 1 matrix. Suppose that when we build our statistical model, we've misspecified, or we have chosen the variance of my x0 to be lambda instead of lambda 0. So I'm doing inference, but I don't know what the variance of my model is. So I've misspecified it. From here, I can write down what all these log likelihood function is. It'll be some square function, so it's the log of the exponential function. And I can write down what the pseudo-maximum log likelihood is. And our problem reduces to maximizing some function, hn of x, which is written on the bottom line, which is given as some quadratic form involving Gaussians, some inner product term with some coefficients given by the corresponding entry of my rank 1 matrix, and some normalization term xi xj squared. And if you're familiar with spin glasses, the very first term in this object is precisely the Hamiltonian of a Sherrington-Kirkpatrick spin glass. And the other ones are think of it as some generalized external field terms. Okay. So this is the type of maximizers and the type of objects we are looking at in the case for the spec matrix. Of course, there's various different ways to specify a spec matrix. This we have specified a parameter of the order 1/square root of n scale. And I guess the takeaway is that the pseudo-maximum likelihood estimator is quite tricky, even in the case of the simplest model. I want to maximize this function. It's a high-dimensional function with random coefficients. The behavior of this maximizer is not an easy object to study. So there's more than one way to misspecify a spec matrix. For example, I could have, let's suppose that my Gaussian matrix, let's say my dye matrix Y was generated conditionally on the spec Gaussian matrix, but my Gaussian matrix has expected value mu instead of 0. So my noise has a mean. And let's say I build a model corresponding to this, but I assume that my noise has 0 mean. If I were to go through the same construction as before, I would get exactly the same objects, but because I misspecified a larger parameter of the model, my last term will now depend on some additional parameters. And the size of the last term is actually much bigger than the rest. So the first three objects, they're of order square root of n. The first three objects are of order n, and the last term is actually of order n over n to the 3 over 2. So depending on how we pick our model, then our scaling or the size of our log likelihood function can actually be really, really dependent on how we define our models. So in this case, if we must specify a very large parameter of the model, then we are really optimizing a very different function. So this general theory is sort of very delicate or very dependent on how we pick our models. And in the last example, let's suppose you have a community detection problem. Again, there would be some Bernoulli matrix. And if we write down the log likelihood function of this Bernoulli matrix, we can see that a function is even more complicated now. It is no longer a polynomial. It has a bunch of sums, a bunch of logs. So in the community detection problem, maximizing this becomes much, much more complicated. So optimizing these can be quite difficult depending on the types of log likelihoods we have. So our goal is we want to develop some unified theory that sort of can tackle all of these problems at once. And that'll be the focus of the next few slides. Okay, so let's introduce some notation. So E of P0 will denote the average with respect to the noise of a model. So in the spike matrix case, this is assuming Y has Gaussian entries. And in the stochastic block model case, this is assuming Y is a Bernoulli 1/2. So this is really the law of the noise, given there is no signal. So it's the distribution of the noise in our model. And we can define three parameters called the information parameters, which you can interpret as the variance of the derivative of the log likelihood, the correlation between the log likelihood of our model and the true log likelihood, and some variance or some normalization term, the second moment of the derivative, the log likelihood of our models. So these are three parameters that sort of depend very weakly on the model. They're sort of the variance covariance parameters. And a fourth parameter, we'll call it the score parameter, which is the expected value of the first derivative of the g. You can think of this as the mean of our model. So these three parameters will be very important later on, since this will actually determine the behavior of all these statistical estimators. Okay. And in the special case, when a model is well specified, so when we're working with the true log likelihoods, then the first three information parameters, they're all functions of each other. So they're all related in a very nice way. And the score parameter will always be 0. This just follows from an integration by parts. So in well-specified model, there's a very nice relationship between these information parameters. But in general, these three parameters are what it is. So what's some intuition behind what these information parameters are? Let's go back to the spike matrix example where our noise had non-zero mean. Our log likelihood function was given by the sum of 4 terms. If I compute what the corresponding information parameters are for this model, beta 1 to beta 4, we see that these parameters correspond precisely to the coefficients in front of each of these 4 terms. So these information parameters in some way encode the size of each of the contributing factors to the maximum likelihood function in the spiked model, in the spiked Gaussian case. Okay. And in general, these parameters are what they are. But in the spike matrix case, they have some nice intuition. They're precisely the coefficients of a log likelihood function. Okay. So now let's state our main result, and here are the main assumptions on our model. So we need our latent variables x0 to be supported on some compact set. And we also need that its empirical distribution converges to some probability measure Q. We're going to be making asymptotic statements, so we need some guarantee on convergence. The space that we're maximizing over also has to be a compact space. And furthermore, we're going to assume that the log likelihoods and the pseudo likelihoods, the G and G0, have bounded fourth moment and uniformly bounded second and third derivative. So once I explain the universality result a bit later, these assumptions will be quite natural. Okay. So what is our first result? Our first result is a characterization of the pseudo-maximum likelihood in the case when the score parameter is M0. So if beta 4 is M0, it means that we have not specified we have not made a mistake in specifying a large parameter of the model. So we've only made a mistake specifying some smaller parameters in the model. And for this case, we can show that the limit of the maximum of the log likelihood converges to the maximizer of some variational formula, which I will explain on the next slide. And furthermore, the performance of my maximum likelihood estimator converges to two quantities, which are precisely the maximizer of this variational formula, of this variational formula in R2. And furthermore, the performance and the limit only depends on our model through the beta parameters, which depended very, very weakly on the actual laws of the Ys. It's only through its expected value of its first and second moment. So the limit of these objects converges to some solution to this variational formula, and the maximizers of this variational formula give you the limiting performance of our statistical estimators because there's similarity and there's norm. So what does this variational formula look like? Well, this variational formula is given as is sort of defined in terms of the maximizer of a complicated function called the PDE. So we're going to call A of S our parameter space, which is the space of increasing paths or increasing functions. First phi is the solution of a modified heat equation, where the initial condition is depends on our parameter space omega. The mu and the lambda are Lagrange multiply terms. And for fixed S and M, which are elements in R2, our function phi is given as the ephemerum over the paths in A, and the Lagrange multipliers mu and lambda of this object. And this is a modified variational formula with some, I guess, with some Lagrange multiply terms or some convex conjugate terms. And the domain of this function is sort of within there, which is sort of the possible values of the inner products of x and the plus x0. So it's the possible values of these functions. So solving this function or understanding this function gives us the performance of the maximum likelihood estimators in the limit. Okay. And so this is the result. So the next question is, well, what happens if you misspecify a large parameter of the model? So what happens if our beta 4 parameter is non-zero? And this happens in the case where we've misspecified the mean of the noise instead of the mean of the signal. So what happens in this case, and the key takeaway is something bad can happen. So if our score parameter is positive and if our latent variables are 0, then you can prove that the cosine similarity between our maximum likelihood estimator and our latent variables will be 0, which means a failure of maximum likelihood estimation. So if I misspecified the mean, there are cases where where maximum likelihood estimator completely fails. And also, if our score parameter was negative and our latent variables were constant, and 0 is in the convex hull of a parameter space. You can also show that there's some cases where, again, the cosine similarity between our estimator and the signal is 0. So failure of inference can really happen if we've misspecified a large parameter of the model. The question is, well, what can we do? Can we modify our model in such a way that sort of avoids these hopeless scenarios? So the reason why there's some complete failure is we want to maximize some function, but the last term is a term of leading order. And this sort of dictates all the behavior. So the natural thing to do is, why don't we just somehow subtract what this term is? And hopefully from there, we can do some nice hopefully from there, we can actually do inference once you remove the bias. And this is very natural in the sense that if I were to recover some sort of spike matrix, and if my matrix had some noise, or if my Gaussian matrix had some mean, then I have this really, really large eigenvalue that sort of just blows up to infinity. I want to remove that large uninformed eigenvalue and focus on the actual eigenvalue where all the information is held. So we want to remove this bad parameter somehow. And how do we do it? Well, we can't remove it directly since we don't know what the parameters are, but we can estimate it. So our estimator for the score parameter will be called this beta 4 hat parameter. And beta 4 hat is our empirical estimator for the score value. And subtracting beta 4 hat should remove the effect of this very large uninformity spike, which is given by the second term. The problem is, at the scale of the problem we are looking at, there's some fluctuations for the beta 4 hat. And these fluctuations are actually on the same scale as the other terms. So we need a further correction. And this further correction is given by this ridge term, this alpha x hat squared. This is a negative parameter that will allow us to tune it and hopefully remove the effects of the fluctuations for this object. So we could define a score corrected likelihood, which is our attempt to do estimation on I guess very poorly specified models.
X bar is just like here.
Oh yes, x bar is the empirical mean, which is just some 1 over n the sum of the x's. Yeah, which is precisely what that second object is. You could write it as 1 over n times I think squared times n if over 2. Yeah. So what can we show is that, well, after looking at the score corrected pseudo log likelihood function, then we can actually have, in all cases, some non-trivial limit, and we have the same result as before, in that the maximum likelihood function converges almost surely to this maximizer of some complicated function that only depends on the beta hat and the score parameter beta 4. And the limit of the performance, so the cosine similarity, converges to the maximizers of the variational formula, and the norm also corresponds to the maximizers. Yes. Oh, alpha right now is an arbitrary parameter of the model. So the maximum likelihood is sort of defined for all choices of an alpha. I see. Yes, the right-hand side will depend on alpha. I should put it there, but we'll see it in the next slide where the depends of the alpha shows up.
Why is it important? Like how large that?
Oh, I see. I guess this is something that we can compute, but it's also point is that this is sort of like a normalization term. So you could compute the inner product between our latent variables x and our x0, but the value of that sort of how big is that, or how does that correlate to how well our estimate performs sort of depends on how large our vectors are. So you want to normalize it. You want to normalize it by the norm, and I guess this gives you some limit for the norm of it. So it sort of allows you to see roughly how large your vectors are. Okay.
Can I ask you,
Yes.
First line, why do you ever want to know like the maximum of the likelihood?
No, you don't.
The argmax.
Yeah, you might want to know the argmax, which is the consequence of 5 and 6. I guess the first one is
so other
different
stuff with
again.
the crazy formulas that do you use it for anything?
Yeah. the value of the max isn't too important, but the maximizers are. So it's interpretation is
Use it to get the max.
that's it. That's it.
Verify the six on the slide.
Yeah. Yeah, the maximizers are the corresponding maximizer of the crazy formula. The actual value of the maximum doesn't have too much meaning.
Where are they in vision? Sorry, I don't see.
Oh, the
Log.
M and the S, they're the
Oh, they're the
maximizers
maximizers.
of the first and second one. Yeah. Yes, and to go to Ben's question, this is the same type of variation of formula. There's an extra term, and this alpha does appear here. So I should have denoted it's behind.
Also, so this madness here.
Yeah.
Can you actually compute this? Like,
We could.
it's hard to tell in 5 seconds. if this
Yes,
is plausible.
so it is computed in certain cases. So the way we actually compute it is you assume that the gamma is a step function, and then this one reduces, or sorry, the gamma is a increasing path. So it's a increasing path. So if I can parameterize the gamma parameter by some number, then this reduces to a multivariable function that we can optimize. And I guess in physics, you basically start increasing the levels. And normally when we do computations, we just do one level or 2 levels to a computer. So in principle, this is compute, but it's tricky.
Yeah.
It is convex in gamma. Yes.
Yeah,
Okay. Good. So now I want to go through just two statistical consequences for, I guess, what were some nice applications for these results. And one is we can actually use it to understand the performance of least squares estimators. So we have defined all these maximum likelihoods, but one thing you can do whenever you have matrix data is your estimator will be your best rank 1 guess. It'll be the vector that sort of minimizes this L2 norm between Y and a rank 1 matrix. So this is called least squares. And essentially, this reduces down to assuming a Gaussian log likelihood function. So I want to find a matrix that minimizes the L2 norm, and we could call this the X hat of LS, which is our least squares estimator. And we'll see what's the performance of this object. And this falls precisely in our framework because this corresponds to a Gaussian log likelihood. So we can actually characterize the performance of least squares in the case when the mean of our data of our noise will be 0. We could find beta LS, which is defined as the correlation between our data matrix Y and the informative and the derivative of our log likelihood function. So this is sort of our correlation between our Y and the way the entries of Y are generated. So in the case that beta LS is equal to square root of beta 0, which is the information of this model, then you get that the performance of least squares is the same as the performance of maximum likelihood estimation. So you achieve the same performance as if you're optimizing the true log likelihood function, even though it may be very complicated. You also have some cases where least squares completely fails in the case that the derivative of my data is uncorrelated with the Y matrix. So in some cases, least squares can fail. And you also have an interpolation between these two cases. So depending on the size of our beta LS parameter, our performance of least squares sort of interpolates between these two cases, and they're given by the maximizers of the corresponding formula. And analogously, if your data matrix Y is not centered, you can do the correction by first subtracting the mean of Y and optimizing over the alpha, over the ridge regression term alpha. And if you do this for corrected models, you could get a very similar choice. So if I choose my lambda parameter in a smart way, and I choose my alpha parameter in a smart way, we can achieve the same performance as optimizing, or as optimizing the true log likelihood. And again, there is the case where it completely fails, in the case where our beta LS parameter is 0. And we also have an interpolation between these two cases in the case where there's some weaker correlation between y and the derivative of g. I guess.
So like you're estimating beta 4 from the data.
Yeah.
Like, is there any way to estimate g naught from the data?
I see. That's a bit trickier in the sense that you are given some data and you want to guess what the law of that is. That's a bit tricky. It's that I don't think there's a nice way to estimate it by the mean or anything. So I could estimate the moments of it, but maybe.
I'm just wondering if there's some way to take a couple moments to improve the
I see.
for g or something.
I see. Yeah, that's a statistical modeling test. I guess it depends on the context of the problem, but I don't think there's a nice quantitative way to do it in general. But yeah, it'll be interesting to see if I can match more moments. Maybe I can build.
Okay, I guess
build that
this thing, like, is there a way to sort of guess that you're in one of the bad cases?
Oh, I see. Can I actually compute this? Yeah, that's I guess one thing you can do is you can always I guess once you do you can always do the correction. So we can always make sure that we're avoiding this. And how to avoid the two case, yeah, that just depends on, I guess if there's a lot of symmetry, then the least squares always fails. I don't know if there's any way to avoid it previously, but okay. So now let's go through some key ideas of the proof. And there's actually two things I want to focus on. So there are two things I want to sort of clarify is one key feature of this result is that four parameters, these beta parameters, these information and score parameters sort of captured all the nuances of model selection. We don't really, the performance is really only dictated by the values of these beta parameters, not by the actual, or it sort of depends very weakly on the log likeness that we chosen. So somehow these beta parameters capture all the information. I want to explain where it comes from. And I also want to give you some intuition of where the psi term comes from. And the first term I'm going to illustrate using some ideas from random matrix theory. And the second one I'm going to use some ideas from spin glasses to sort of give you some ideas from these objects. Okay, so let's begin with the first one. So how can these four parameters capture all the nuances of model selection? And the analogy I want you to keep in mind is the central limit theorem, which says that if x1 and xn are ID random variables, and I know its variance is sigma squared, then the sum of my xi is appropriately normalized converges to some limiting object, and this limiting object depends only on the mean through its normalization on the left and its variance. So the limit of this quantity depends very, very weakly on the law of my x's. It really only depends on the first and second moment in some way. And a very similar phenomenon happens in the high dimensional case, which I'll try to illustrate. And I'll be demonstrate this through topics from random matrix theory. So random matrix theory is the subfield of probability theory that studies matrix valued random variables, which is precisely the types of data matrices we are looking at. And the type of universality that we see here is something called spectral universality, which says that if I have a matrix with IID entries where the let's just suppose that the mean of my entries are 0, the second moment will be sigma squared, and the fourth moment will be finite. If I look at the empirical distribution of the eigenvalues of the matrix of Z, then you know that its empirical distribution converges to some limiting object called the semicircle law, where the semicircle law, the distribution only depends on sigma squared. So the empirical distribution of the eigenvalues will be supported on some semicircular distribution. You can think of this as the analog of the CLT for random matrices. And what we want to do is we want to sort of show a similar probability holds for spike matrices or data matrices that sort of generate conditionally on some rank 1 spike. So how do we do that? Well, we're going to define a quantity called the free entropy. You can think of it as a smooth approximation of the maximizer. So our maximum likelihood is the maximum of this log likelihood function, but you can approximate it through the 1 over n the log of e to the sum of the log likelihoods. If I scale my determining exponent with L and make it very, very big, then the integral on the right sort of concentrates on near maximizers of this object, which is what we have below. So L will be a scalar parameter that you can take to be very, very big. So I'll put the L in front of this object. So it's the you can think of it as we are introducing a temperature parameter of the model. So we don't have to do maximum likelihood estimation. We could just look at the free energy with some temperature parameter L. And because you have this nice bounding or nice approximation, we could just study the free entropy instead. And what we could show is we could show universality at the level of the free entropy function. So let's see what I want to do now. I just want to remind you what type of limiting object we will be working with. So the spike matrix model is actually the model that encodes all the difficulties of the problem we need. So this will be our limiting object. So remember that the spike matrix model had a specific form of the Gaussian log likelihood. For simplicity, we're going to assume that beta 4 will be 0, but the same analysis can be done even with the beta 4 parameter. So we're just going to assume that we have a it's a score unbiased model. So this would be our Gaussian log likelihood, and let's define a general class of Gaussian log likelihoods where we just replace these coefficients with T1, T2, T3. So this gives us a sort of generalized class of limiting objects that we want to work with. And what we could show is, or what we could define is, we could define the corresponding free energy with respect to this generalized Gaussian model, where we just replace all the coefficients, these T1, T2, T3 parameters. And what I showed last year with at least Guillet, Florent, Krezakala, and Borova is that the limit of the free energy of our original model with our log likelihood functions, if I pick beta 1, beta 2, beta 3 to be precisely the Fisher information parameters, then I can show that in the limit, the difference between these two free energies are very, very small. So it suffices to only compute the Gaussian model where the parameters in front of the terms are given by the information term and the information parameters. F0, okay, F0 was a space of the log likelihood. So we needed that the fourth moment of the derivative of the log likelihood was bounded, the second moment was bounded. So it's basically, I need Taylor's theorem to hold, and I also need the universality result for band matrices to hold as well. So I need the fourth moment to be bounded. So if my log likelihoods are well behaved, then I can show that the free energy of my Gaussian model is a good approximation of the free energy of the true log likelihoods. And just a remark, we actually proved something a bit strong. We also showed that the law of the cosine similarity under the procedure satisfy the same large deviations principle. So we can actually show something a bit more precise than universality of the free energy. We can show that the cosine similarity is also universal, but this fact is not needed. Okay. Good. So the main takeaway is that these high-dimensional likelihoods are essentially the same, or the performance of these high-dimensional likelihoods are essentially the same as the likelihoods of spiked Gaussian matrices, where I guess all the parameters of these models are now given by these information parameters. So these play the role of your variance of our data. It's the variance and the covariances of all these objects. And the behavior of these sort of encodes the limiting behavior of my Gaussian function. Okay, great. So let's go for, well, where does this psi function come from, and how can we compute this object? So the analogy I want you to keep in mind is, I guess in elementary probability, something called the quantity called the moment generating function sort of completely determines the probability the distribution of x. And we want to say that something very similar happens, that the quantity that we are computing sort of encodes the behaviors of the maximum likelihood and the behaviors of the cosine similarity. Okay. And our way to explain this will be using some techniques from spin glasses, which is the subfield of conduct matter physics that studies disordered magnetic states and complex systems. And these complex systems will be very similar to the types of functions we want to optimize. Okay. Okay. So from before, we want to optimize what this. We have reduced the problem to computing the to understanding the maximizers of these Gaussian log liquids, since these maximizers are for universality the same as the log liquids we wanted to study before. They compute what this object is. I could just find Gaussians. I switched the notation halfway through because W's and G's were overloaded, but I probably should have been. Oh, they'll also be Gaussian. So even in the Bernoulli case, this would be always Gaussian. The Bernoullis will show up in the T1 parameters, but not through the noise. It will always be Gaussian. So the free entropy will be the quantity that we want to compute. I'm going to compute this quantity for all parameters T1, T2, T3. So the link between this problem and spin glasses is if I ignore the second and the third term and I just replace the first term with beta, then the object that we want to optimize is precisely the Hamiltonian of a Sheraton-Kirkpatrick spin glass. And the limit of this object was computed by Parisi and was computed by Parisi, and actually won the Nobel Prize in Physics in 2021. And it shows that the limit of this free energy is given by some theorem over some space of parameters, which is very, very similar to the objects that we showed before. And mathematically, this is proven by using Guerre's interpolation and the methods of Talleyrand in 2006. And many of the techniques that we use in the proof were sort of formalized by Panchenko in 2011 through ultrametricity. And what we did in 2023 is, well, we computed the same limit in the presence of these two extra terms, and we used techniques from large deviations theory to sort of compute what this object is. And because we have some extra terms, this is where we get, this is why our object sort of looks like some convex conjugate of something. It is from the techniques from large deviations. And to compute the maximum likelihood estimation, it is sort of what happens when you take the parameter L to infinity. We just have to understand, well, how do I take the limit of these finite temperature models to infinity? And if you understand this limit in a smart way, you can get the performance of the maximizer as well. And this is our current work with Curtis and Okosh. Good. So our main takeaway is that statistical physics sort of gives us the technical toolbox to actually compute this limiting object, to sort of compute what the limit is, and also characterize the performance of the maximizers. So all of the machinery to compute the limits of the maxima of these objects really relies on tools from spin glasses. Okay. All right. So this is just a reminder of a main result, that we have some limit for the maximum of the molecular functions, and we have some limit for the cosine similarity given in terms of the maximizers of this function. And the key steps to our proof is to study the maximizers. It suffices to study the free entropy functions and send the temperature to 0 to get the maximum likelihood estimate. By universality, it suffices to compute the Gaussian version of this problem. We don't have to worry about the complicated maximizing complicated functions, since its limit will be the same as the Gaussian model. We can use tools from large deviations and spin glasses to compute the finite temperature object of this function. And we can recover the maximum likelihood object by taking the gamma limit of the right-hand side because of this approximation of the maximizer. Okay, great. And generalizations, I don't think I have time for generalization, so let's skip this for now. And the question is, well, what's next? So what's some future problems related to this model? So some future directions is, one is the algorithmic consequences. So the performance of all of these statistical estimators only depend on the beta parameters, but when we're actually doing optimization, then it really doesn't depend on the types of log likelihood as you choose. So if I were to maximize the log likelihoods, maximizing these type of functions really depends on these certain log likelihoods. But what we showed is that we can sort of understand the performance if we choose different log likelihoods. What happens if we always choose Gaussian models? Those are perhaps easier to optimize than these log functions. So there will be some trade-off between the complexity of the log likelihood function we want to study and the loss of accuracy by choosing an incorrect model. So hopefully this some type of analysis will allow us to sort of smooth out our landscapes or choose likelihood functions that are numerically easier to solve without losing too much accuracy. All of our analysis was also done for rank 1 objects, but some interesting models involve planted tensors or higher rank spikes. So we want to generalize this to higher rank models. And a last problem is we want to understand what the difference between maximum likelihood estimation and pseudo-maximum likelihood estimation is. And there's a conjecture in physics in the sense that when you're dealing with maximum likelihood estimation, your optimization problem actually simplifies. It becomes replica symmetric. And as soon as you misspecify your model, then your model becomes replica symmetry breaking. So this some type of framework is sort of the first step in answering this physics prediction, which really encodes the, I guess, how does the performance of statistical estimators, how does it depend on model selection, which involves just understanding the maximizers of these complicated variational formulas. And I think that's it. So thank you. Thank you for your time.
Questions?
Yes.
So we thought about like what happens if you do the EM algorithm on those examples. So like you do your estimation, but then you update lambda based on like the lambda, which is like, so update the model to try and get closer to model specification and see, because I feel like that's what
I see.
statistics people do.
Yep. I see. So